Hi, how are you doing? My name is Lonnie. Today we're going to talk a little bit about stoichiometry. This tends to be a subject that for many students, regardless of whether they're college students and or high school students, at times tends to be a little more difficult. Hopefully these processes that I share with you will be beneficial in you and make it a little more, at least mentally, much less fatiguing. Okay, one of the first things in talking about stoichiometry, let me identify a chemical equation, and I'm going to use this chemical equation throughout my process here. Now note, we've got iron on the reactant side plus oxygen, diatomic oxygen, which yields iron 3 oxide. Now we've got to understand what exactly does that mean. There are several interpretations on any chemical equation, and let me start with the very first one. Well, first we can interpret this as iron plus oxygen yields iron 3 or iron oxide. Number one interpretation. The second thing is we can interpret it in terms of particles slash atoms, molecules, and in this case formula units. Here's the second interpretation. 4 atoms of iron plus 3 molecules of oxygen yields 2 formula units of iron 3 oxide. Hence our my second interpretation. Now let's go to the third one. This third interpretation is going to interpret that equation in terms of moles. Now moles is significant when we're doing stoichiometric problems. And so hence, let me move forward on this. Number 3 interpretation, 4 moles of iron plus 3 moles of oxygen yields 2 moles of iron oxide, iron 3 of course. Third way of interpreting that. The last and final interpretation is let's interpret it in terms of the law of conservation of mass. Now what does that mean? That means that whatever we start with, we must also end with it. We cannot create nor destroy matter, mass. And so hence, let's go ahead and interpret this. If I do the molar mass of iron, I'll get approximately 4 times 56, which is approximately 224 grams on the iron. If I take the oxygen, O2, 32 by 3, gives me approximately 96 grams, which totals 320 grams on the reactant side. Okay? Let's go ahead and take the product side. I'm going to take the iron 3 oxide, 1 molar value, if you will. 2 times 56, 112. 3 times 16, 48. 112 plus 48 gives me approximately 160 times 2 gives me 320. And so hence, what did we identify? Well, first of all, we've identified that the chemical equation in fact is balanced. And secondly, hey, we have not destroyed the law of conservation of mass. It once again is still intact as we've identified. What we started with, we certainly ended with it at 320 grams. Okay, let's go ahead and move forward. This next concept is identifying, let me rewrite this chemical equation. Of course, I'm going to use this throughout the problems that we work, in terms of stoichiometric problems that we work. And this next concept is identifying what they call mole ratios. So in other words, what information does this give to us in terms of a ratio of one item versus another item? Okay, mole ratios are, when we're talking about a ratio, we're really just talking about a proportion of comparing one thing versus another thing. So the first mole ratio, I'm going to take iron, and I want to compare iron to my reactant, my other reactant, which is oxygen. That mole ratio, in fact, would read, let me write it, 4 moles of iron to 3 moles of O2, and hence, this is my relationship, iron to oxygen. Now listen, we can invert this also. And so hence another relationship, as opposed to iron to oxygen, we can flip this and reverse this and do oxygen to iron, which gives us 3 moles of oxygen to 4 moles of iron. Hence we've got 2 different ratios here. Now note, with any one of these reactants as well as the products, we can do a relationship. I can compare the oxygen not only to Fe, but I can also compare that to the product. So likewise, I can take the iron and I can compare the iron to the product. And so hence, there are 2 other relationships there, and inverting them gives another 2 other relationships. So total in this particular 2 reactant, 1 product gives us approximately 6 different mole ratios. Let me write one more to perhaps clarify this. Let's take the product, iron oxide, and let's compare it to oxygen, O2, and let's compare it also to Fe. So having said that, I'm going to take, comparing the iron oxide first. So 2 moles of iron oxide, and I'm going to compare it to the O2 versus 3 mole of the oxygen. Hence, there's one comparison. Now note we can invert this and we can compare, instead of the iron oxide to the oxygen, we can compare the oxygen to the iron oxide. And so hence this would be inverted, and it would hence be 3 mole of oxygen to 2 moles of iron oxide. Another relationship. Then let's now compare the iron oxide to the iron. Let me scroll that up just a hair. Scroll that up. So I'm going to compare the iron oxide here to the iron. Here, scroll that down just a hair. Okay, so hence I've got 2 moles of iron oxide to 4 moles of iron. And so hence another mole ratio of the product to one of the reactants. Now note we can also take this, so we can invert it, and we can compare that particular reactant to the product, which in fact would give us, instead of 2 to 4, it would in fact give us 4 to 2 ratio. These mole ratios are significant when we are taking a mole value that's given and moving it to a mass value, or a mass value and moving it to a mass value, or a mole value moving to a mole value. So let's go ahead and let's start on, we've already talked about the interpretation, we've also talked about the mole ratio relationships. Let's start with our stoichiometry. The first one that I want to identify is a mole to mole stoichiometric problem. Okay, I'm going to refer to the abbreviation of mole, which happens to be MOL. Use an arrow, mole to mole. Okay, this would be our first stoichiometric problem that we will work today. I'm going to use the same equation, chemical equation, 4Fe plus 3O2 yields 2 Fe2O3. Okay? Now, what do we do in these problems? First of all, in the word problem that is given us, we want to first identify the given, we want to identify the mole, the unknown, and then we want to go ahead and put it in our step process and calculate. This being a mole to mole. When I say a mole to mole, what do we mean? That means that we are starting with a mole value and we are going to end up with a new mole value for some other reactant or product. In this case, let's identify what our given and unknown is. And I'm going to symbolize the given with a G. So I'm going to use my iron, in this case, here as my given. And my unknown, let's solve for the iron oxide as the unknown. It's going to be a mole to mole. And let's say, for example, I'm given 4 moles of Fe. That's my given. 4 moles of Fe. And I want to know how many moles will 4 moles of Fe convert to the number of moles of iron 3 oxide. And so hence this is my, if you will, that's what I'm solving for. So our first step is take the number of moles given, 4 moles of iron given, and that's my very first step. The second step is utilizing the conversion factor, which in fact would be the mole ratio. Remember the mole ratios that we just did previous to this. Take the mole ratio of the product unknown to the given Fe. Okay, and so hence we utilize the coefficients by doing this. So hence we use the unknown to the given. The unknown, of course, is the 2 moles of the Fe2O3 to my known, which was given 4 moles of the iron. And hence, let's put parentheses just to kind of separate these two steps. And that will, in fact, give us the number of moles based on the mole ratio of 2 to 4. Well, let's go ahead and calculate this and cancel down to 2. That 2, this can be broken down to 2. So we have 2 times 1 divided by 1. So hence we come up with 2 moles of Fe2O3. And there is our solution there. Very fundamental quantitative problem. Step 1, the given. Step 2, the mole ratio. And then hence our answer, what we were looking for. That's the first type of stoichiometric problem, mole to mole. All right, let's move ahead. Let's do a second problem here. This next problem is going to be a mole to mass. Okay. Now, note, any time that you have a mass, we know that we're dealing with molar values. So hence we want to calculate the unknown of the mass that we're looking for. We want to calculate the molar mass of that because essentially we're going to need that to ultimately get to mass. Let's go ahead and write our equation again. 4Fe plus 3O2, and that's going to yield me to Fe2O3. Okay, let me scroll that up. Give us a little room here. Again, this is a mole to mass. Let's switch. Let's make this our given, okay? Oxygen is our given. And let's make our unknown, let's make our unknown again. We'll make our unknown the iron 3 oxide. Okay, I know that with the unknown, this is ultimately the mass that I need to calculate in grams. Note that mass is, the unit is grams. So from the very beginning, I'm going to go ahead and do my molar mass for the Fe2O3. That's what I'm going to first calculate, okay? So again, this came out to, for one of these, 56 by 2 is 112. 112 plus 48 gives us approximately 160 grams per mole. 160 grams per mole. Okay, so far, and this is really the only item that we need in terms of molar mass. Do we need the given? No, we started with moles, so we don't need to really do the molar mass of O2. If we did, hence O2, 32 grams per mole. Let's scroll that up a little and continue. Okay, let's see where we are. All right, let's identify, let's say for example we were given, let's say 2 moles, okay? So the amount that we're given is 2 moles of O2, so let's start this problem. Well, the first step is identifying the given 2 moles of O2. Okay, I'm going to put that over 1, kind of put it in a proportional or fractional format. My next step is to identify the mole ratio, unknown to known. Unknown in this case happens to be my product, which is 2 to 3 to the given or unknown, so hence I have 2 to 3. Now listen, essentially I'm just going to go ahead and write down the proportion here, 2 to 3. But note that that 2 to 3 designates or symbolizes 2 moles of the unknown iron 3 oxide, and that 3 designates 3 moles of the O2, which in this case is the given or the known. Okay, that's my second step. Now this is one more step that we have to identify, and that's converting. Once we get to this point, we're really at the moles of the unknown. Going to this next point, we want to multiply times the mass of the unknown, which is mass of the Fe2O3, and our mass happened, we already calculated it at 160 grams per mole. And so hence, let's see what we have. We can, let's see, we've got 4, let's take our calculator on this. We got, let's see, 4 divided by 3 times 160, which in fact gives us approximately 213.3 grams of Fe2O3, and hence we have just completed the second type of stoichiometry type problem, a mole beginning with a mole and ending in mass, in this case on the iron 3 oxide, which came to approximately 213.3 grams of iron 3 oxide. And that is the second stoichiometric problem. Now let's move forward, let's do another one. We're going to continue, and now we're going to start with mass and we're going to end with mass. This is our third stoichiometry or stoichiometric problem. I'm going to use the same equation, 4Fe plus 3O2, and that yields, of course, 2 formula units or 2 moles of Fe2O3. Let's switch up. Let's get a different given. Let's get a different unknown. Let's make the given here of the iron 3 oxide, and let's make our unknown. Now let's make the, how about the iron? We'll make that the unknown. Okay, and on the given, let's say that we are given approximately, how about 320 grams of the iron 3 oxide will be our starting point. Okay, so let's go ahead. Well, now remember, because we start with mass, my given, which in this case happens to be the iron 3 oxide, I need to find the molar mass for the given, but I'm going to mass also the unknown in this case, which happens to be Fe. I can look at my periodic table and get the molar mass of that. Let me go ahead and write this. I'm going to use M for the symbol that represents molar mass. So the molar mass of Fe2O3 per mole, and it happens to be 160 grams per mole. The Fe, I'm going to round this up a little, make it a little more rounded, if you will, 56 grams per mole. Note, if you look on the periodic table, it's 55.85 grams. Okay, so we've got our molar mass. Let's go ahead and extend this a little so we've got some room. All right, what is our first problem? Well, the first step in this mass-to-mass problem is identifying the given. So hence my given is 320 grams of the Fe2O3. Okay. Well, I'm going to take that 320 grams and I've got to convert it to mole. So how do I do that? Well, I divide by the molar mass. So we know what the molar mass is, 160. So let's divide this by 160 grams, and hence there's my first step. Well, I've got that. Now I want to move into a ratio between the unknown and the known. And in this problem, of course, our unknown was the iron. My known or given was the iron 3 oxide. So hence my mole ratio, which is my next step, would in fact be the unknown to the known, 4 to 2. Let me drop that down to 2 to 1. Same thing, quantitatively it doesn't affect the problem. So it's a 2 to 1 ratio. Again, this really indicates 2 moles of iron per 1 mole of iron 3 oxide. Again, all I've done is abbreviated that and utilized the coefficients. Let's continue on to the next step. Well, the next thing, once I've gotten to this point, which in fact is moles of the unknown, I need to multiply by the grams to get my mass of the unknown. Well, the number of grams per mole happens to be for iron is 56 grams per 1 mole. And then we can come to a solution on this. Well, let's see. 160 here, this is 2. 2 times 2, that's 4. 4 times this gives us approximately 224 grams of iron, and hence my solution for a mass-to-mass stoichiometric or stoichiometry type problem of 224 grams of iron. Again, let's go through this step. Take my given. The given happened to be 320 grams. Convert those grams to mole by dividing by its molar mass. Use the conversion factor, which is my unknown to known, 2 to 1 in this case, multiplied by the unknown's molar mass, 56, and hence arriving at 224 grams of iron. All right, let's look at one other problem. Let's go with the limiting. This is the last problem that we'll do. Let's go with the limiting reactant problem. Okay, limiting reactant. Now I'm going to use the same chemical equation that we've been using, plus 3O2 yields 2Fe2O3. What is a limiting reactant problem in stoichiometry? Well, as you know, most chemical reactions will not go at 100%. In other words, all of the reactants that are present initially will not all proceed forth into 100% of product that it yields. And so typically, there will be a reactant that is all used up, that hence will, in fact, impact the amount of product that is produced. But it will also have a reactant in that you will have some excess, or as known in this type of problem, an excess reactant. So what are the solutions that we want to find on this particular type of problem? First, we want to find the limiting reactant. Second, we want to find the excess reactant. Third, we want to find the mass of the unknown, which will be the product in this case. And fourth, we want to identify the excess not used of that particular excess reactant. Okay, so let's start with my givens are going to be specified with the G. In this case, the limiting reactant, it's always the reactant. So iron and oxygen are both reactants I'm going to give us. My unknown, once we ultimately U or UNK for unknown, is going to be the iron 3 oxide. So let's, one of the first things that we want to do is identify the molar masses of all 3 of these, because we ultimately will have to use it. Okay, so let's do, I'm going to do big M. molar mass. Let me extend this just a little bit. And for the iron, for the Fe, it is equal to 56 grams per mole. For the O2 is equal to 32 grams per mole. And for the, which we've used a couple of times, for the iron 3 oxide is equal to about 160 grams per mole. We've got our 3 molar masses. Now, we specified what the givens were, which in this type of problem, it's always the reactants. Let's give a value to this, and then we can proceed forward and calculate the 4 solutions that we originally spoke about. Well, let's say that we're given 10 grams of iron, plus, let's go 10 grams also of the oxygen, and this, of course, is my unknown, so this is my question mark here. Well, the first step that we want to take in identifying the limiting reactant versus the excess reactant is we want to translate the given grams into mole value. Okay? So we take our given, we take the given, here's the iron, right here, iron, oxygen. We take the given, so I'm going to identify iron on one line and then I'm going to identify oxygen on the other line. And then I can keep these numbers straight. It's important that you keep these numbers straight so it isn't so convoluted and all of a sudden you get tied up and you can't work the problem. So keep these numbers straight by identifying iron on one line, O2 in this case on the other line. Well, we were given 10 grams of iron. We were also given 10 grams of oxygen. And so the first step is to divide it by our molar mass. We already calculated our molar mass for iron, which was 56, and for oxygen was 32. And let's get a value of this. Let's see what our values will be. 10, of course, divided by 56 provides us with a mole value of 0.1787. I'm going to use that mole value there. And then let's take 10 grams divided by 32, and that in fact gives me 0.3125. Great. Okay. Now, what do we do from this? Well, in order to get a ratio of these, in 1. It's much easier to identify the ratio in terms of something to 1. Let's take the smallest value and divide both of these values. Okay? So if I in fact divide both the values by 0.1787, this gives me 1. Divide this by 0.1787. Let's find out what our value will be on that. Divided by 0.1787. That value happens to come out to 1.748. Okay, and so hence the relationship of these, of the iron versus the oxygen, is in fact 1.748 to 1. I'm going to put it in that particular format here, 1.78 to 1. This is the O2 right here, and this happens to be the iron right there. Now, let's compare this actual, notice I used that, ratio to the theoretical mole ratio in our original chemical equation. So let's pull up to this. Now note, our ratio, and in this case I believe I've got oxygen to the iron, is a 3-to-4 ratio. Iron to oxygen. Yes, iron to oxygen. It is a 3. Let me write that down here. There's a reason why I'm writing it down here. There's one. Now that 3 to 4 is really 0.75 in a decimal format. So essentially I have 3 to 4, 2, 0.75 to 1. And this is the actual mole ratio taken from the balanced equation. 3 to 4 or 0.75 to 1, 3 to 4. Now, here's where we determine the limiting reactant and also the excess reactant. When we look at this, we know that we have 1 here, we have 1 here, which happens to refer to iron, and so here we have enough. Fe, we've got enough there. We don't have too little, we don't have too much. Well, now we're going to look at the O2. And this O2, the actual ratio is 0.75 from the balanced chemical equation, but we in fact have 1.748. So that tells me that I have actually got too much of the O2, 1.748, compared to 0.75, what I actually need. So hence this O2 will be my excess, abbreviation for excess, and the iron in fact will be the limiting reactant. So we have now just solve two of the solutions. We've identified the limiting reactant. We've also identified the excess reactant. And now we're good to go for the third one, which is calculating the mass of the product. And that will in fact be a mole to mass problem. Now you've got to ask yourself, well, what's my starting point on this? Well, our starting point happens to be the mole value for the limiting reactant, which in this case happens to be Fe. Let's go back to find out what our mole value is. And here is the mole value that we originally calculated based on the given, which was 0.1787. And this particular mole value will be the mole value that we use for the next two mole to mass problems in ultimately completing this limiting reactant problem. So my first step, in fact, is going to, let's extend this one more time, 0.1787 moles. Again, this is moles of Fe, okay, 2:1. The next one is the relationship of Fe and iron 3 oxide. And that relationship, in fact, mole ratio would be 2 to 4 or 1 to 2. 2 to 4 or 1 to 2. So hence I'm going to put it in 1 to 2. And then I'll need to multiply by the molar mass of the iron 3 oxide, which happens to be approximately 160 grams per mole. And then let's see if we can't, oh, this could cancel out too. We've got 80 times, let's see, 0.178 times 80. And that provides us with approximately 14.24 grams of iron 2 oxide. And this is the amount of product that we produced from the original 10 grams of iron and 10 grams of oxygen, 14.24 grams of iron 3 oxide, and hence our third solution. Great, we're almost there. Let's finish this thing up. Well, the next thing is we want to identify how much excess do we have. And our excess, as you recall, was in fact the oxygen. Limiting was the iron. So we want to find out how much did we use. So hence we're going to do a mole to mass with my unknown being the O2, and my given in this case, of course, is going to be the Fe, or the mole value that we originally calculated. So let's go scroll that up just a little. So that's our starting point on this. Again, this is a mole to mass. The mole value, as I indicated originally, the mole value that you use for these particular problems is the mole value, actual mole value calculated of the limiting reactant, which in this case was iron. So we start with 0.1787 moles. Again, that's of Fe. I'll just put that up here, over 1. Then the relationship of oxygen to iron, which happened to be 3 to 4. Okay, 3 moles of oxygen to every 4 moles of iron, and that was multiplied times the molar mass, which happened to be 32 grams. And then we've got our solution there. Okay, let's see if we can divide here. There's 4, this is 8, so 24 by 17. See, 0.1787 times 24, which in fact will give us 4.288 grams of O2 used. Key point. 4.288 grams of O2 used. Well, if I used that, what did I start with originally? And so we're almost there to our final answer. Okay, well, we originally, as you recall, we started with 10.0 grams of O2. Well, in this problem, guess what? All we used was 4.2, so let's minus this, 4.288. From the original 10 that was given, and we should get approximately 5.712 grams of excess, not used O2, and hence my solution, last solution, solution number 4 for this limiting reactant. And we appreciate your time, and we'll be back. Thank you.